designed, the word is designed to make you think, forces that obey the law of conservation of energy. That's why they're called conservative. It's actually a little bit misleading, because all forces obey the law of conservation of energy. But conservative forces obey what you might call the law of conservation of mechanical energy, a restricted form of the law of conservation of energy. Anyhow, that's what the word is for conjure up in your mind. Conservative forces. Force is conservative if the work it does is independent of the path taken. Work it does on what? On some object. As the object. From point A to point B is independent of the path taken. It's the same for all paths, in other words. Doesn't matter which path you took. So here's the point A, and here's the point B, and you're planning to move some object from point A to point B in the presence of some force, maybe the force of gravity or something. If the work necessary to push that thing from point A to point B is independent of the path you take from point A to point B, that force is called conservative. This seems like a very peculiar sort of kind of force, but that turns out to be the critical feature of a force as far as conservation of energy is concerned. Is the work it does when an object moves from point A to point B the same for any two paths from A to point B? And so it's called a conservative force. Example of a conservative force, the force of gravity in this room. The amount of work it takes to move an object from this point to this point here is mgh, where h is just the height difference between the two, and it doesn't matter which route you went from A to B, it's just going to be mgh period, where h is the difference in height between the two. So gravity is the classic case of a conservative force. Kinetic friction, on the other hand, is the classic case of a non-conservative force. If I move an object from there to here in the presence of friction, the amount of work I had to do that time was not very much. But if I went by a circuitous route, I would do a whole lot more. So kinetic friction, the amount of work you do, depends entirely on how you went from point A to point B, not just on what the two final points are. So, e.g. gravity, but not kinetic friction. Second item, potential energy. Another piece of funny sounding language, because potential energy always sounded to me like not quite bona fide energy, you know, the kind of phony stuff. It's energy is just as much as any other kind of energy is, over potential is very ill-chosen. But potential energy, suppose you've got a conservative force. The potential energy at some point P is the amount of work I would have to do to move the object in question from some fixed reference point up to the point P. So, given a conservative force F, the potential the work I must do fighting against F. objects from some fixed reference point O to the point P. That's a mouthful. What does this mean? Here's some reference point O, just something that you and I have agreed on beforehand. For today, boom, that corner of the room is our reference point for all potential energy. The potential energy at some other point now, at this point here, is the amount of work it would take to move the object in question, this block of wood, from that reference point up to the point P in question. Formally then, U, the potential energy at the point P, is equal to minus the integral from the reference point up to the point P of F dot dr. At the very end last time I was making a string of comments on that definition. First, how come the minus sign out in front? The minus sign is out in front because the definition of potential energy is the work I have to do, not the work that the force F itself has to do. I was fighting against F, so the force I'm exerting actually is minus F. We could write it like this, but it seems cumbersome. U of P equals plus the integral from 0 up to P of F me dot dr. That's the force I exerted, but F me is equal to minus the F, the force that was exerted by whatever gravity or whatever we're talking about there. So this is the same as minus the integral from 0 up to P of F dot dr. I always find that signs in this business a nightmare. In fact, in a moment, we're going to come to an example where there are no fewer than 4 minus signs that all conspire and come out of the Y. That's my job, keep track of the minus signs and to explain to you from time to time why those minus signs are in there. But it is awkward. The way to think about it is always remember that the potential energy is the amount of work you had to do to assemble the system, if you like. The amount of work you had to do to get the system into the state that we're talking about. To move the object up to where it's supposed to be from where it was starting from. So there's the minus sign. Second point, the reference point there. It doesn't matter what reference point you use. How come? Because it turns out only differences of potential energy matter in physics. Only differences of potential energy, and when you calculate the difference in potential energy at one point and at some other point, then all reference to the point 0 drops out. That will become more clear later on, I think. But, so don't get alarmed about the reference point here. It is true that potential energy is by its nature ambiguous because you've got to decide at the beginning what is your reference point, and that's pretty arbitrary. However, in practice, it's only differences of potential energy that ever matter, and for those, the reference point drops out. Third item, why did I have to say for conservative force here? I had to say conservative force because if you've got a non-conservative force, then this integral would depend entirely on how you went from O up to P. The amount of work done would depend on the path you took from the reference point to the point in question. Therefore, this wouldn't define anything. Somebody else could get a completely different answer to what potential energy is at some point by taking a different route up there, and that wouldn't do this. Simply would not define a function of the point P if the force is non-conservative. So this whole game, you just can't do it for non-conservative forces. There's no such thing as potential energy for kinetic friction, for example, or for any other non-conservative force. So it's a subtle point, but the whole argument, the whole notion of potential energy is out the window if you didn't have a conservative force to begin with. Okay, now I'm going to run some examples of potential energy. The first example, not going to be any surprise. Actually, the second example is not going to be any surprise. The third one perhaps will be. y is equal to 0 at the floor level. By the way, having said back here, I meant to say that although the reference point is arbitrary, in the sense that only changes in potential energy ever matter, and for that the reference point drops out, in most problems, a natural sort of reference point actually suggests itself. There are rare exceptions where this is not true, but most of the time, any two sensible people would agree on what is the reasonable place to put the reference point. For instance, in this room, if we're measuring gravity in this room, let's work from ground level. It would be kind of stupid to work from 2 floors below if everything is going to be taken. In this room, we could do it if it was a sensible place. Suggests itself floor level. So we'll take the reference point at floor level, that is to say, at y equals 0 in my diagram. Now, what is the potential energy of a height h above the floor now? That is, according to the definition, minus the integral from that reference point, 0, y equals 0, up to the height h, that's where I'm calculating the potential, of f, but f is minus mg, and it points in the j hat direction, in the y direction, actually minus y direction. So the only component of the r that matters in the dot product is the component of the displacement in the y direction. Do you see how I got that? No dot product anymore. If you want to be very fussy about it, you say f equals minus mg j hat, and you say dr, the displacement, is dy, well, in general, it would be dx in the x direction plus dy in the y direction, whatever displacement you did in the x direction, plus whatever displacement you did in the y direction. That would be the most general element of the displacement element. But in this case, the x in the dot product, the j hat here, is just the j hat component of dr, so it's minus mg dy. Makes sense? I'm doing this in gory detail, even though we actually know the answer. These two minus signs cancel out. I get mg, the integral from 0 to h of dy, and that's nothing but h itself. So this is mg h. There's a gravitational potential energy in this room at a height h above the floor, using the floor as my reference point. Make sense? We have seen that formula before, a couple of times actually. I called it carefully the gravitational energy before, but we now see that it's just a particular case of potential energy. It's gravitational potential energy, the potential energy associated with gravitational force. Second example. Spring. So imagine that I have here a spring on a nice frictionless surface, by the way. I don't want any friction in the problem. And let's let this be the x direction. And the force is the force exerted by the spring. What is that? Yeah, the force exerted by the spring. You remember the formula from Hooke's law? It's proportional to the amount by which the spring has been stretched. And the proportionality constant is k, the spring constant, so it's k times x. But let's be very careful about the signs now. The force on this thing is back in this direction. If it's been extended out an amount x, the force is back toward 0 extension. It's equal to minus kx, then in the I-hat direction. So minus kx I-hat is the force that's acting on the object by the spring. Of course, in order to pull that thing out, I must exert a force to the right on it, in the plus x direction, but the force it's exerting is in the negative direction, minus x direction. Make sense? Let's see. I'm supposed to calculate now the potential energy of that spring when it's been stretched out a certain amount, let's say an amount d. our reference. First thing you've got to decide in calculating potential energy is what reference point will you use. For the spring, what is the natural reference point for the spring? The natural value of x. Zero. Equilibrium, not stretched at all. That would seem like the sensible place to define as your reference point. Use x equals 0. No stretch. Seems like a sensible way to do business. Okay, now the potential energy relative to that reference point, if it's stretched out an amount d, is equal to, from the definition, minus the integral from the reference point, which we chose to be 0, out to the point b of f, which is minus kx. And this time it points in the x direction, so the only component I want for dr is in the x direction. That would be dx. Once again, the two minus signs cancel. I get k from the other reference constant times the integral from 0 to d of x dx. What's the integral of x dx?
1/2 x squared.
1/2 x squared. So this is 1/2 k x squared, evaluated between the limits 0 and d. At the upper limit, I get 1/2 k d squared, and at the lower limit, I get nothing. So this is 1/2 k d squared. That's the potential energy of a spring that's been stretched out amount d. We, again, encountered that case before. I just derived it before I remember, or just stated it as the spring energy, what I was then calling spring energy, 1/2 k x squared is stretched out an amount of x. So it's the same formula that we had before, but now we recognize that that formula, 1/2 k x squared, actually is a particular kind of potential energy. That's potential energy associated with a spring. MgH, potential energy associated with gravity. And any conservative force that you want, that you come up with, there is an associated potential energy. Third example is actually back to example number 1 again, in a way. Gravity. What's wrong with this calculation that I did before? Well, this is perfectly fine if you're right near the surface of the Earth, where the force of gravity is indeed mg minus mg. Mg is 9.8. But what if I'm, 10,000 miles above the surface of the Earth? And you know that the acceleration of gravity g is much weaker out there, and therefore this formula, which just assumes that g was constant all the way out, was 9.8, no matter how high you get above the surface of the Earth. That's fine if you're working in this room or even up to the top of the skyscraper or something like that. But it's no damn good if you're talking about way far away from the Earth. Then I have to take into account the fact that the force of gravity itself is increasing as you go higher and higher. Make sense? So, here's the Earth. And now I want to go way far away. Let's let that be the x-axis. And I'm actually interested in knowing what's the potential energy if you're way out there, let's say at a distance r from the center of the Earth. So you understand why this is okay locally, but no good for large distances. If I'm doing an astronomical problem, the motion of planets or something like that, then this is nonsense because the mg is just close to the surface of the Earth. the general case, what if you're far from the Earth, so the force of gravity is no longer mg, what's u at a distance far from the center now? Well, I need to know what the force on an object is here. Let's say that the Earth has a mass capital M, and this is an object that has a mass little m. What was the force of gravity on that? Do you remember? Let's see. Let's say take the general case where this is out at a distance x from the center of the Earth. Then the force acting on it would be g, the constant of universal gravitation, the product of the masses, m times capital M, divided by the square of the distance away it is. As a vector, what direction does that point? If x is to the right, what's the direction of the force on an object right there at point x? It's inward, right? It's actually in the negative x direction. So if I'm being very careful about the signs here, this is minus I hat. There's the force on the object if it's at a generic distance x from the center of the Earth. So far, so good.
Why was it a negative?
Why is it negative? Because the force is attractive. This object here is attracted toward the center of the Earth, so the force is in that direction. And the way I've set the problem up here, that's the minus x direction. Of course, I could have put my axis here and running back, but it seems awkward. It's more sensible to start your x-axis at the center of the Earth. In that case, you're committed to it. The force is actually negative. Minus x direction. Okay, what's the potential now at the point R? The potential energy of that object at point R. Well, I've erased it, but it's minus the integral of f dot dr from the reference point down to the point in question, or up to the point in question, R. In this case, it is minus the integral of f is itself minus g m over x squared. And now I want just the x component of the displacement. That's dx. And what are the limits? Well, the reference point. You know what? I don't know in this problem. I do, but let's pretend that we don't know what is the natural point for to choose as our reference point in this case. I'm just going to call it R0 for the moment, okay? We'll decide when we come to the end of the problem what was a good choice for R0. I want to go from R0 out to R, and I'm not committing myself yet to what R0 is. So this setup, right? It's minus the force of gravity, minus gmm over x squared, times the displacement, dx. Once again, the two minus signs cancel out. I get g, m, all that stuff comes out in front, times the integral of 1 over x squared dx. And I'm going to evaluate that at the limit R0 and then at the limit R. And that will tell me the potential energy at point R relative to a reference point of R0. So far, so good? Anybody spot that integral? 1 over x squared? No, you think 1 over x would be the log. 1 over x squared is actually a whole lot easier. This is x to the minus 2.
Minus 1 over x.
It's 1 over x, actually minus 1 over x. Minus 1 over x. Is that right? Let's check it. That's minus x to the minus 1th power. If you differentiated that, we'll pull down a minus, which kills that minus, and lower this down to the minus 2th power, which is exactly what I wanted here, x to the minus 2. So the minus sign is necessary to kill the minus sign that would come from the differentiation. So the integral of 1 over x squared is actually minus 1 over x.
You can actually apply the rule if you recognize 1 over x squared as x to the minus 2.
Right.
And the rule for x to the n is to...
For integrating?
For integrating. Increase the n from minus 2 to minus 1 and bring that new value, minus 1, in front of the whole thing.
Perfect.
So it really follows exactly the rule. You don't need to
Right, right. The exception is 1 over x. That's where all the rules fail. You just gotta go to its logarithm suddenly. All of the others is 1 higher power, and the way I think of it, whatever factor out in front you need to make the derivative come out right. So, minus 1 over x, yeah. So what Herb says is right, there's nothing exceptional about this case at all. If there's an exceptional, except that we're more used to dealing, I guess, with integrals of positive powers, so it's a little bit funny in that sense. But if you think of this as x to the minus 2, then it's just like all the others. So, evaluated limits r0 and r, this would give me minus 1 over r at the upper limit, minus a minus, a plus 1 over r0 at the lower limit. So what is the potential energy here? The potential energy of an object of mass m located at a distance r from the center of a large object of mass capital M. The answer is g times the product of the masses times minus 1 over r plus 1 over r0, where r0 is the distance from the center to the reference point. There is u. Now, you tell me what is the best choice for the reference point in this problem. Now that we've done it for a generic reference point, what's the good choice, the clever choice? You might say, well, center of the sphere, of course, x equals 0. That would be a great choice. What do you think of that? Not a good idea, because then I would have to divide by 0, 1 over 0. So, r equals 0, r0 equals 0 is not an acceptable reference point. What would be more acceptable? Yeah. Well, 1 meter, 1 fathom, 1 what? You can keep talking. What is the natural length in this problem? You might say, well, how about the radius of the sphere? Let's go from the surface of the sphere. That would be perfectly okay, but then you would have a 1 over capital R in your formulas, and that would be awkward to carry along. Somebody has already said it. There's a very clever place to put the reference point in this problem, which is infinity. If I use infinity as R0, then 1 over infinity is 0. That term drops out entirely, and I've got the cleanest possible formula, the cleanest expression that money can buy for this. Choose R0 equals infinity. That is to say, I'm putting my reference point at infinity. Then 1 over R0 goes to 0, and I have a nice formula, u of r equals minus, don't forget the minus sign, minus g times the product of the masses divided by r, just one factor of r. One factor of r. It's kind of like the formula for force itself, but that was gmm over r squared. This is gmm over r. How about that? This is the potential energy then in the large frame, when you're talking about points way far away from the Earth, the potential energy of an object of mass m located at a distance r from the center of another object of mass capital M. What is the potential energy in that case? Well, it's always the amount of work it took to assemble a system. The amount of work that it took me to bring this particle in to a distance r from the center of the Earth, if you like. Bring it in from where? From way the hell out there, all the way out at infinity. So I think of it like, you know, God has a storehouse out there at infinity of all the masses you ever might want to work with. Okay, I'm going to grab one out at infinity, pull it in, shove it in, and slap it down at the point R. How much work did I have to do? Boom, minus gm. What's the minus sign got to do? Why is there minus there in that sense? Well, you know what? I didn't have to do any work at all fighting against gravity. On the contrary, the rock wanted to be there. All I had to do was let it go, and I could harness it up and have it do some work for me. That's what the minus sign is. this as a handy way to remind yourself of the minus sign in there. You're always starting from a mass out at infinity. How much work did you have to do to shove that in and stick it down a distance r from the other mass? A negative amount of work, because it loved to be there, is attracted there. The force of gravity pulled it there, and so you had to do actually a negative amount of work. Now I'm going to run a couple of applications of that formula. The first one, calculating the escape velocity from the Earth. I think you've probably encountered this problem before, or even listening to news when they launch rockets or something like that. It's usually put this way. Suppose I throw a rock straight up. How high is it going to go? Well, it goes up a little ways and then it runs out of steam and comes back down. But throw it a little harder. Rises up higher. Throw it really hard. Could I throw that rock so hard that it never did come back? Let's call it an escape. Well, if the force of gravity stayed constant at the value mg, then no matter how hard you throw that rock, it's always going to come back. In fact, we know how high it would rise. This is a problem we've done often before. It starts at the ground with a velocity v, so its original energy is 1/2 mv squared, and it rises up until that's all converted into kinetic energy, mgh, and that tells me how far this thing is going to rise. The m cancels out, and I get h equals v squared over 2g, and it doesn't matter what v is, there's always some maximum height that it's going to turn around and come back and hit you on the head. But this isn't quite right, because gravity in fact doesn't stay constant. It gets weaker and weaker as you go on. So this raises a very interesting question. Given that gravity does decrease the further out you go, is it just conceivable if you threw that rock hard enough, it would never come back? I think a priori that's an interesting and unobvious question, whether rocks always would come back no matter how far you, how fast you throw them, even granting that gravity gets weaker and weaker, or on the contrary, is it the case that if you throw it hard enough, granting that gravity gets weaker, it'll go away and never come back? The fact of the matter is, it is possible to throw a rock so hard that it never comes back. And my business now is to calculate for you exactly what that velocity has to be so that a rock would never come back to the Earth. So, but gravity decreases, so what's the actual calculation? Let's run conservation of energy on using this formula for the potential energy instead of mgh. That's the whole part. So, here's the object at the surface of the Earth, and I throw it up with a speed v, and I ask you, what is its total energy at the moment of launch? Well, it's got kinetic energy, 1/2 mv squared, and it's got potential energy too. In this game, it didn't have potential energy because I was starting potential energy from 0, using reference point of floor level or ground level. Here, I don't use ground level, I'm using infinity as a reference point, so it had some potential energy even at the beginning, namely minus gmm, divided by the radius of the Earth, because that's how far it was from the center at the beginning, right? So there's E initial, the total energy. Yeah?
Why do we say minus?
Minus because the potential energy is negative gmm over r. That's this minus sign here.
Does it have to do with the direction of kinetic energy?
No, wait a minute. Kinetic energy doesn't have direction. Kinetic energy is always positive, half mv squared. Doesn't matter which direction you're going. Kinetic energy is always positive. Potential energy can be positive or negative. In the gravitational system, using infinity as reference, it's always negative because it always required a negative amount of work for you to move something into the gravitational field of some other object. It was always attracted there. So the gravitational potential energy is always negative. In this scheme, if you had used the surface of the Earth as your reference point, then that would be true. Initial energy. How about the final energy later on? Let's just say that this is somewhere on this rock's journey. As it goes out there, it's getting slower and slower as it goes out, of course. So E at that point would be, this is the initial energy, 1/2 mv final squared, the kinetic energy it has out there, minus gmm over r final. That would be the final energy. And now let's see, what do I want for the final destination of this thing? I'm interested in the case where it just barely makes it out to infinity. What would the kinetic energy be as this rock pulls into the station at infinity here? 0. Of course, if I threw it even harder than that, then it arrives out there at the station at infinity with some leftover kinetic energy. Big deal. I want to know what's the bare minimum that I can throw this with, that it just gradually is coming to rest as it comes out to infinity. I don't know exactly how to say that, right? But I think of a train station out there that says infinity on it. And this thing is just barely pulling into the station and run out of steam just when it arrives at infinity. What's the potential energy when it gets out there?
0.
0, right? Because that's infinitely far away. Again, I'm dividing by infinity, so this is 0. I want this to be 0, just barely arrives, and this equal to 0, of course, it's way the hell out there. So the total energy that I want is 0, when it just barely makes it out to infinity. I could give it more than enough, of course, by throwing it more than the escape velocity, then it would arrive out there with more energy, but I'm talking about the bare minimum. Just barely to make it out to infinity. That's when I want the total energy of the system to be 0. Well, if the final energy is 0, the initial energy must have been 0. So I get 1/2 mv squared minus gmm over r equals 0. That's the condition for escape. Well, what's that tell me? What I was trying to find out was what that velocity had better be in order for it just to make it out to infinity, what that launch velocity would have to be. If you're a rocket engineer, how much fuel do you have to load on this thing to get it going fast enough? Well, 1/2 mv squared equals gmm over r. If I pull that over to the other side, the little mass cancels. How about that? Doesn't matter whether you've got a rocket or a Mack truck. When you're launching, the launch velocity would be exactly the same. Multiplied by 2, v squared equals 2gm over r, or v is equal to the square root of 2gm over r. I had intended to calculate this for the Earth, but I now suddenly realize I did not bring the radius of the Earth. Does anybody know what the escape velocity is from Earth?
I think it's about 25,000 miles per hour.
Miles per hour. It's Neanderthal. Miles per hour. It's a pretty good clip, anyhow. Fast. Sorry, I don't remember what the number. I know what the number is, but you can work it out.
It's the square root of 2 times the near-Earth orbital velocity.
Oh, yes, that's right. Or I could also do it from the point of view of, yes, I can do it like that, because I know what little g is. Let's see.
still need to,
M
you need the
over R
radius of
squared.
You need a radius of here.
That I do know.
Okay, good.
And so GM over R is actually equal to RG.
And now you know.
So this is equal to square root of 2 RG. Okay, so V escape for the Earth is square root of 2 times the, no, wait a minute. I still need the radius, it's the mass I brought. Ah, forget it. We can do
Well,
it.
the
This
radius,
is 4,000
the radius,
kilometers.
the radius is not so hard to figure
What? 3,000?
Yeah, plus that.
out. A meter is 1 part in 10 to the 7th of the quadrant, by definition. So,
The circumference?
pi over 2 times r is 10 to the 7th meters.
That's it, pi over 2 because it's
1 quadrant.
2 pi r, where all of pi over 2 is 1 over 10 to the 7
Pi over 2 times, pi over 2 times r is 10 to the 7th meters,
is 10 to the 7
I believe.
meters. Pi over 2. Yeah, because 2 pi r is the entire circumference. Pi over 2, okay. So r is 2 over pi times 10 to the 7th. How about that? Okay, so B is equal to 2 times r, that's 2 times 10 to the 7th over pi times g, that's 9.8. Yes, we can do this. Okay. 2 times 10 to the 7th divided by pi times 9.8 equals, take the square root of that, and you get 1.12 times 10 to the 4 meters per second, if I did that right. So that would be 11.2 kilometers per second. That's a pretty good clip for the surface of the Earth, but possible in principle. In the early 19th century, Laplace speculated on the following interesting question. What if you took the Earth and squashed it down so small that the escape velocity became equal to the velocity of light? Then his notion was, you shine a flashlight up, even light wouldn't be able to escape because it's going at the speed of light. If the escape velocity is the speed of light, if you squash down the Earth that much, the light would just barely escape. Squash it down even further, the light would go up, and then it would fall back down and hit you on your head. What would the radius of the Earth have to be in order that even light could not escape? I want to put in speed of light for escape velocity is equal to root 2gm over r, or squaring both sides, c squared times r equals 2gm, or r is equal to 2gm over c squared, where c is the speed of light. People ridiculed Laplace at the time, saying, don't you know that gravity doesn't affect light? It's just stupid. Light just takes off and gravity doesn't pull it back at all. So Laplace took that section out of the second edition of his book, but it turned out to be a very clever idea. And in fact, this is what we now call a black hole. Is an object so compressed that the escape velocity is equal to or greater than the speed of light. Then nothing can get out of that thing, and it would look black from the, supposedly from the outside, because no light can ever get out of it. What would the radius of the Earth be if the Earth were a black hole? If you took the Earth and squashed it down like a snowball or something like that, it would be 2 times G, that's 6.7 times 10 to the minus 11, times M, the mass of the Earth, which I did bring with me, 6 times 10 to the minus 24 kilograms. Divide that by C, which is 3 times 10 to the 8 meters per second squared.
What's the mass of the Earth?
Very good point. There was a public error of 48 factors of 10. Not too bad for an amateur. Okay,
That's 10 to the 8th or 10 to the 5?
10 to the 8th. We're talking meters per second.
Oh,
If you
meters,
use
meters,
kilometers
okay,
per
okay,
second.
okay. Yeah.
Okay, 2 times 6.7 times 10 to the 11th minus times 6 times 10 to the 24th plus divided by 9 times 10 to the 16th equals 9, actually 8.933 times 10 to the minus 3rd meters, which is 9 millimeters. So if you took the Earth and squished it down till it was 9 meters in radius, 9 millimeters in radius, 18 millimeters in diameter, almost 2 centimeters in diameter, about that big, a largish marble. If you squished the Earth down that tight, the Earth would become a black hole. The escape velocity would be the speed of light, and no light would get off the Earth. Not a practical thing for the Earth, but supposedly this is the terminal state of certain kinds of stars. I have your exams, but so that it won't be chaos, what I've done is got them in alphabetical order, and I'll put them out here by sections.